Hello. This lecture will cover pages 20 through 22 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 2, Kirchhoff's Current Law. If you take a look starting on page number 20, that's where we're going to be, you're going to see Kirchhoff's Current Law. It's also pronounced Kirchhoff's Current Law, but we're going to refer to it as simply KCL in this course. KCL is one of the 5 most important laws in electrical engineering. In almost all your analytical courses, you'll use KCL. It's extremely important. When we get to nodal analysis, you'll see its usefulness. Let's discuss it. At any junction point or node in an electric circuit, the algebraic sum of the currents entering the node must equal the algebraic sum of the currents leaving the node. Think of that. If you take a point in an electrical circuit, any currents coming into that point has to equal the currents coming out. And it can be shown mathematically this way. The currents entering have to equal the sum of the currents leaving. We're going to use the assignment where currents entering a node will be positive and the currents leaving the node will be negative. Some textbooks do it differently. The textbook that we're using in this course does it just the opposite way. But we're going to stay with the convention where currents entering the node are positive and currents leaving a particular node will be negative. There's really no difference in the system equation information. In other words, when you get an equation at a particular point, one will just be the negative of the other, but it'll have the same useful parameter information in it. So it really makes no difference which way you assign the currents, but we're going to assign it this way in this course for consistency. Now you can say KCL another way. You could say the algebraic sum of the currents entering and leaving the node is 0. And you show that mathematically this way. At a particular node, the algebraic sum of the currents is equal to 0. K goes from 1 to n different branches or different currents. Now, you can see this expression here from this one up above. You just bring the sum of the currents leaving over to the left-hand side, and you get the algebraic sum of the currents entering and leaving the node have to equal 0. These are the same expressions here, really. So let's take a look at it. Here we have a point in a circuit. We have current I1 coming in, I2 coming in, and I3 going out. Can you take a look at this, and can you say at the node, by Kirchhoff's current law? On an exam or on a test, you're going to write at the particular node. Let's identify this as node 1. So at node 1, by Kirchhoff's current law, we get a plus I1 because it's coming in, plus I2 because it's coming in, minus I3 because it's leaving equals 0. That's an equation. That's a node equation at that node 1. Let's take a look at it in a little bit more detail. Here's a circuit. Take a look at that circuit. And what I'm going to have you do is I'm going to have you write an equation using Kirchhoff's current law at node 1, at node 2, at node 3, at node 4, and at node 5. Let's do the first one together. I'll write at node 1 by Kirchhoff's current law. Now, make it real clear. On every homework assignment or on any exam solution, I want to see this statement written. I want to see at node, whatever node point you're writing the equation at, comma, by KCL. And I want you to write the equation. So can you look here at node 1, by Kirchhoff's current law, and can you see a plus I1, minus I2, minus I3, because I3, don't forget, is leaving, and coming down through here, equals 0. Try node 2 on your own. Can you get this? Can you look at this and see at node 2 here? You'd say at node 2 by Kirchhoff's current law. Or at node 2. So I have a minus I1 because it's leaving, plus I4 because it's entering, and a minus I6 because it's leaving, equals 0. And before I move on, check how many currents go in and out of that node. 1, 2, 3. So you better have three currents represented. 1, 2, 3. So you don't miss any. That's a good check. Let's look up here. How many currents? 1, 2, 3. And there they are. 1, 2, 3. Now I want you to go ahead and take a piece of paper. This step, to be able to do this, is very, very important for nodal analysis, which is coming up. You have to be able to do this. It might look simple, but I want you to try it on your own. Try it at node 3, node 4, and node 5, and see if you get the rest of my equations right there. See if you get the rest of my equations. Continuing on. Let's take a look at example 2. There's example 2. There's another network, and I want you to find I1, I4, I5, and I6 using Kirchhoff's current law. And here's the answers. Well, let's take a look. Let's do a couple of them. First thing I do is I assign nodes. I already assigned the nodes for you. I assigned a node here, a node there, a node there, a node there, and a node here. And a node here. There's my nodes. 1, 2, 3, 4, and 5. So, at node 1, by Kirchhoff's current law, so you have to write this, at node 1, comma, by Kirchhoff's current law, colon, I get a plus I1. That plus is important. Don't forget the plus up there. It's entering. Plus I1 minus 60 milliamps minus 20 milliamps equals 0. And I can solve I1 equal 80 milliamps. Now, look at the other nodes. And where do you know 2 out of 3 currents? Or 3 out of 4 currents? Well, I moved on to node 5. Why did I move to node 5? Because I look down here at node 5, and I know this current, I just don't know I6. That's the unknown. So, at node 5, by Kirchhoff's current law, I get a plus I6. I6 is coming in. Take a look at it. Let me see if I can't get this all on here. A plus I6, a plus 40 milliamps, and a minus 30 milliamps equals 0. You have to take your time and do this very carefully. You solve this equation for I6, you get minus 10 milliamps. See if you can't move on to I2 and I3, or move on to node 3, move on to node 2 by Kirchhoff's current law, and see if you can get 70 milliamps for I4. And then either at node 3 or node 4 by Kirchhoff's current law, see if you can get I5 is equal to 50 milliamps. See if you can get those answers on your own. How about example 3? Now in example 3, I wanted to point something out to you. Example 3 is really example 2. Here's example 2, and there's example 3. Well, they don't even look alike. How are they the same? Because what we're doing is, I'm referring to this point right here. I'm going to refer to this point. Let's see if I can't find it here. I'm going to refer to this point right here, and I'm going to call that a surface area. Or that could be another whole circuit. I'm going to call that a whole circuit up here, right here. Network 1, I called it. And I'm going to take this point right here. I'm going to take points 3 and 4, this area here. I'm going to call that another network. There could be a lot of things in this area. Not just the resistors here, or what. It could be transistors, it could be resistors, it could be diodes, it could be capacitors. But I'm going to put that all in network 2. And then I have my 60 milliamps going between the networks and my 20 milliamps going between the networks. And I'm keeping this point here, this point 5, this down here. So we're trying to get you to understand this works not only at a point, but in a whole surface area or in a whole network. The currents going into the network or coming out of the network have to equal 0. So see if you can use example 3 here, and there's what we're looking at. I want you to use Kirchhoff's current law to find I1, I4, and I6 up here with these networks. And there's the answers. If you take a look, there's my equations in my solution to the answers. Notice in each case, I said at, in this case, it's at network 1 by Kirchhoff's current law, at network 2 by Kirchhoff's current law, at node 1 by Kirchhoff's current law, because this point here was a node. This was a node. It wasn't, I didn't have a network in this example. I had a point. Now on the exam, to get full credit, you have to write this. You have to write this, so I know what your equation is telling me. You have to write this, so I know what these equations are telling me. You have to write this. That's the third time I said it, so it's important. Let's take a look at some other examples. Here's example 4. I want you to find I1 in this circuit here. That's a network of some sort there. Now, when you do these examples, write equations. If you just give me an answer on an exam and it's wrong, it's all wrong. I can't give you any extra points, any extra credit. So you have to write equations. That's why, that's the reason we're taking our time in this simple lecture on how to use KCL. So write an equation, see if you get I1 equals minus 50 milliamps. What about example 5? Here's example 5 here. Okay. I want you to go ahead and make a node here. What I would suggest is this is all one node right there. Call that node 1. Put a point here and call that node 1. Because this point, these are all the same point. So pick a point. And let's refer to that. Maybe it's easier to see if you do it this way. There's node 1. The currents entering and leaving that node have to equal 0. Write the equation and see if you can get IT equals 70 milliamps. Now, most of you could go ahead and do this in your head. You could say, well, wait a minute. What's IT have to be? Well, if I sub t has to be equal to 10 milliamps plus 40 milliamps plus 20 milliamps. It has to be 70 milliamps. Even though you can do it in your head, I want you to write the equation in terms of IT. That's the building block here. How about example 6? Write an equation at this node here using Kirchhoff's current law and find I1. See if you get that answer. How about down here? You have a node at this point. I'll help you out on these examples. I'm going to call this point node 1, and I'm going to call that point node 2. Okay. This is a reference point down here. This is also a node down here, but it's going to be our ground reference. That's all. That's a node 2. There's 1, 2, 3 nodes in this circuit. Here's 1, here's 2, and 3's down here. But we don't need to write an equation at this reference node. You can get the information here and here. So I want you to start at node 2, write an equation at node 2, see if you get I1 is 8 milliamps. Write an equation at node 1. And in terms of KCL, see if you get 5 milliamps. You have to be able to do this on your own. Here's example 8. I want you to use Kirchhoff's current law, write an equation using KCL, and find I sub x. Whatever I sub x is in this middle resistor. You don't even have to know the resistor. The current over here, the current in this current source, that's not a voltage source. That's a current source. It's 10 Ix. So that's how you refer to that current. The current leaving here, coming down through here, and coming back here. That current right there is 10 Ix. That's what you put in your equation. You're going to have one equation with one unknown. You get Ix equal 4 milliamps. Right there at that node 1. And down here in example 9, what I'd like you to do is take your time at this node point right there. You could do it at this node point, but I'm going to make that a ground reference down there. Let's do it at this node up here. Make that a whole one surface area. And write a node equation using KCL. Write the currents here, 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 and here. You'll have one equation with one unknown, and you'll get Ix equal 12 milliamps. If you can work these 9 examples, it's going to set you up perfect down the road for nodal analysis, which is an extremely analysis tool in electrical engineering. And that concludes this lecture.